Hello, Dr. Bans here. So let's look at the Fourier transform of these standard signals. I call them standard signal because square wave is always standard, unit step signal is standard, and rectangular pulse is also standard. Okay, so they are standard signals. So let's see about the first one. All right. So in the first one, we're going to have the square wave. Okay. So the square wave is such that x of what? T. We're going to find their Fourier transforms. X of t is equals to square, okay, of what? T. Okay, so this is the square wave. Okay, and then let's represent it. So now here you're going to have here to be what? 1. This is the square wave of t. And then this is how the square wave is like. Here is minus 1. Okay, so here is minus infinity, and then here is infinity. Here is t. Okay, all right. Okay, so now this is a square wave signal. Okay, so now here, whenever we're dealing with standard signals, the first thing we do is that we try to see if it satisfies the Dirichlet condition. As they are Fourier transforms, we have to use another method to find it. Okay, so now it's a standard signal. So let's see, checking for the Dirichlet condition. So the Dirichlet condition is such that it should obey this one. So their integral should be less than infinity. So the integral of this particular x of what? T, okay, should be less than what? Infinity. Okay, dt should be less than infinity. Okay, all right. So now let's see. So we're going to have this one infinity minus infinity. Okay, so the square wave. Okay, so the square wave here is going to be, let me say, square of what? T. Okay, it's supposed to be actually less than the infinity. Okay, so like this one. Okay, so then in this case here I can have dt. Okay, so here actually I can break this one into two. Into what? Into minus infinity to 0. Okay, into basically it's a pulse signal. So plus what? Here 0 to what? Infinity, and it's also delta what? T. Okay, so now let's see, if you put these ones inside, what are you going to get? Okay, you're going to actually have 0 minus infinity, okay, plus infinity minus 0. Okay, basically, which is actually equals to what? Infinity. Okay, so if we have something like this, obviously it does not satisfy the what? The Dirichlet condition. It does not satisfy the Dirichlet condition. So that means that we must use an indirect approach. Okay, so does not satisfy Dirichlet condition. Okay, okay, so now use indirect. Okay, indirect approach. Okay, it's a standard signal, indirect approach. Okay, to find the Fourier transform. Okay, so now to use the indirect approach to find the Fourier transform, we will use this one, e of, okay, we use this one here, we will use e of minus a mod t, okay, into what? Square of what? T, okay, into square of t, okay, into this. Okay, so we're going to use this one. So if we have this one, then it's going to be the integral of what? Infinity minus infinity. Okay, e of minus at. Okay, here is mod. Okay, into square, into square of what? T, into e minus j omega. Okay, e minus j omega t. Okay, omega t. Okay, dt. Okay, so this is what we're going to have. Okay, so now here basically the square is a pulse, so it's 1. so we can eliminate it, and then we can have here like this, okay, e minus a mod t into what e exponent what e j what t dt. Okay, so this one can be equals to here what we can have is that we can have it to be from minus infinity to 0. Okay, minus infinity to 0, and here I'll take the negative of this t. If I take the negative of this t, negative times negative, it will be positive. So I'll have e a what t into what into e exponent minus j omega t. Okay, but this aspect, you see, one aspect of the signal is below the negative, is at the negative side. So here, let me bring this negative here. Okay, and then plus this one 0 to what infinity. So here, let me take the positive side of this mod. Okay, so the positive side of this mod is going to give me minus 80, because here is positive. Okay, at the first instance I took negative aspect, because negative of negative t times negative a will be positive what 80. Okay, all right, so the next instance I'm going to take the positive aspect. Negative a times positive t will give me negative 80, okay, times this one. Okay, e exponent minus j omega t dt. Okay, so basically these are the two instances that we have to actually look at to be able to consider this, one. So this negative is such that this part is within the negative domain. Okay, so now when I have that one, then what I can actually do is that I can just have negative 0, a negative here is minus infinity. Okay, and then to what 0. Okay, so e exponent what e exponent here I can just factorize out. Okay, I can just factorize out, and it will be what a minus what j omega t. Okay, dt plus what let me just do it fast. 0 into what infinity. Okay, here I can just factorize out, and then I'm going to have minus a plus j omega t, okay, dt. All right, so this is what I'm going to have. Okay, so if I have okay, let me put equal to here. Okay, so if I have this one, then I just have to go on straight away and then integrate. Okay, so if I'm going to integrate this function, then I'm going to actually have 1, okay, 1 over, but there is a minus here also, so it will be minus 1 over what a minus j omega, okay, into what e exponent what e exponent a minus j omega t. Okay, and here the limits are what minus infinity and 0 plus, okay, plus what I'm going to get here. Okay, so here it will be plus minus 1 over what a plus j what omega into what e minus a, okay, into a plus what j omega what t. Okay, and here, okay, here the space is limited for me to write my limits there. Okay, so let me just continue with on another page. Okay, so this is basically what I was going to write. That I was going to write minus 1 a minus j omega, okay, into e a plus please, I'm going to write minus 1 over a minus j omega into e exponent a minus j omega into what t. Okay, the limits here is minus infinity and 0, plus what plus minus 1 over a plus j omega into what? E exponent minus a plus j omega. Okay, here is what? 0 and then what? 0 and then infinity. Okay, 0 and then infinity. Okay, so basically that is what I'm going to have over here. Okay, so please, you have to be aware that here is what? Infinity. Okay, all right. So I'm sure you are aware why I'm getting all those ones. Okay, so here why I'm getting this one is because here I have negative here because of this negative that came here. Okay, and then here I have a negative here because if you bring this one down, okay, if you are integrating this one, you get minus 1 over what? A plus j omega. Okay, so minus 1 over a plus j omega into this one. Okay, so now I'll just introduce in my limits. Okay, so we have done similar things before, so no need to waste time at all. So we have minus 1 over a minus what? J omega into what? E exponent what? 0. E exponent 0 is what? 1. And then e exponent what? Minus infinity. Okay. E exponent minus infinity is what? 0. So let's say 0. Okay. And then here we can have what? Minus 1 over what? A plus what? J omega. Okay. And then we're going to have here I can put this one there. Okay, so we're going to have what? E exponent what? Minus infinity. E exponent minus infinity is what? 0. And then E exponent what? 0. Okay, E exponent 0 here it will be minus what? 1. E exponent 0 is 1 and this negative, so it makes it what? Minus 1. Okay, so it's going to be E exponent minus infinity because of this what? Negative. Okay, and then so what I'm going to have is that I'm going to have minus 1. Okay, I'm going to have minus 1 over what? A minus j omega. Okay, here it will be positive, negative, negative, positive, plus what? Here it became negative because of this place. Okay, but here it's positive because of this negative and negative. 1 over what? A plus what? J what? Omega. Okay, so when I do that, then I'm going to have minus 2 over minus 2j omega. Okay, if you have this one, then you're going to have minus 2j omega, and then I'm going to have a squared plus omega squared. If you take the LCMs, you'll be able to know why it is coming like that. Okay, so now here I'll just proceed from here. Okay, so I'll just proceed from there, and then proceeding from there, what I'll be able to do is that, and now I know that the Fourier transform of what? The Fourier transform, okay, of E exponent minus A mod what? T, okay, mod T into what? Square of what? T, okay. The Fourier transform actually is giving me, the Fourier transform is actually giving me minus 2j what? Omega, A squared plus what? Omega what? Squared. Now, if I want to make here 1, okay, if here is 1, then the square, 1 times any number is that same number. So if here becomes 1, then actually it will not have any influence of the square, so that I'll get the square alone. To make here 1, I'll make here A to be what? 0. So let's say that A is approaching what? 0. Okay, so if A is approaching 0, then that means that this place will become what? 1. Okay, this place will become 1. Or better for understanding, if A is approaching 0, it's better I think it's better I put the A here. Okay, it's better I put the A here. Okay, and then also basically I'll put the A here, and then also here also become 1. Okay, because I'll have here to be E exponent what? 0 into what? Square R of what? T, which will give me the Fourier transform. If here A is approaching 0 here, then that means that I'm going to get minus 2j omega on what? Omega what? Squared. Okay, so in that case, I'll get square R of what? of t, okay, into Fourier transform. Okay, here what will happen is that this this one will cancel each other. Okay, this one will cancel each other. So what I'm going to have is that omega will cancel omega. Then I'll have only one omega here. So I'll have minus 2 j omega. Sorry, please, sorry. I'm going to have square r of what? T, Fourier transform. Okay, I'll have minus 2j, okay, over what? Omega. Okay, but you have to also know that in terms of complex numbers, this j, I can bring it down so that it will become positive. So square of what? This square t, okay, which is my signal, which is the square wave, is going to be what? 2 on what? J omega. Okay, 2 on what? J omega. So this becomes the what? The Fourier transform for what? The square wave. Okay, so now this question is completed. All right, the question is completed. We have found the answer, which is 2 on what? J omega. Okay, so now let's go to the second aspect of the second question that we were asked. Okay, so our second question that we were asked was that we should find the Fourier transform. This is II, or number 2. Number 2, the Fourier transform of what? Unit step signal. Okay, the Fourier transform for unit step signal. Okay, so we're going to do that. The Fourier transform for unit step signal. So a unit step signal is always like this. Okay, here is what? T, and then here is u of what? T, and here is what? 1. Here is what? 0. This is a unit step signal. Now let's see if it satisfies the Dirichlet condition. So here, to satisfy the Dirichlet condition, here we can put minus infinity here, infinity here. Okay, so we can just have x of t d what? dt. But when it is a unit step, this place x of t is what? 1. Okay, so in that case, I'm going to have delta of what? T into what? Minus infinity into what? Infinity, which is going to be equals to what? Infinity minus what? Infinity, which is equals to what? Which is equals to infinity. In that case, it is not obeying the what? The Dirichlet condition. Why is it not obeying the Dirichlet condition? Since we don't have a definite value for the what? For the integral. The integral is supposed to be less than infinity, but now it's equals to infinity. That means that it's not obeying the Dirichlet condition. So we have to use an indirect approach to find the standard Fourier transform. Okay, so the indirect approach that we have to use, we're going to do it soon, does not satisfy the Dirichlet Dirichlet condition. All right, does not satisfy what? The Dirichlet condition. Okay, so now we use some indirect approach. So the indirect approach we can use here, we're going to use it this way. Okay, so here I can say that here is what? I can have this one, which is what? Half, and then this place is u of what? T, which is half, and then I can have this one also, which is also what? Half. Okay, but here is minus. Okay, and then here is what? T. Okay, so this one is for what? This half is for the square wave. Okay, and this half can be for let's say 1. Okay, for the unit for 1. Okay, the half of 1, because half of 1 will actually also give you this one in the negative. Okay, so now here what I can say is that the Fourier transform, okay, the Fourier transform for my function, which is u of what? T, is going to be equals to half of what? Half of the Fourier transform of what? 1, which is this aspect, okay, plus half of the Fourier transform of what? Square wave. Okay, which is what this part, okay, which is this part, okay. Or you can even interchange it. You can make the square wave here and then the other one also here. It doesn't matter, okay. But in my case, I'm taking half of one to be here and half of square wave to be here, okay. So here I'm just going to have here square of what t, okay, like this, okay. Now what I can actually do again is that what is the Fourier transform of 1? Okay, the Fourier transform of 1, we've got it to be what? 2, we've got it to what? 2 pi into what? Delta of W. That's one we have found it before, so you can visit our previous lectures and be able to know. So now here Fourier transform of u of t is equals to what? The Fourier transform of 1. Okay, the Fourier transform of 1, that one we got it to be what? 2 pi into delta of what? W. So half of that. Okay, so half of that. Okay, and then plus the half of the square wave. So the square wave, we got it to be what? We just found that one. We got the square wave to be what? 2 on what? J omega. Okay, so these two. So now basically that means that the Fourier transform for u of t, okay, is going to be half of this one is going to be what? Pi delta of what? Omega. Okay, pi delta of what? Omega. And here is going to be what? 1 over what? J what? Omega. So this becomes the what? The Fourier transform for what? For unit step function. Okay, this becomes the Fourier transform for unit step function. So here now I can write that unit step, okay, has a Fourier transform, okay, of pi of delta of what? W plus 1 over j omega. All right, so this completes this aspect. Okay, so now let's find the other aspect also. Okay, so the last aspect of the question. Okay, so now the last aspect of this particular session is going to be the Fourier transform for a square, for a rectangular pulse. Okay, so rectangular pulse, we write rectangular pulse like this: pi. We write a pi on, so Fourier transform of rectangular pulse, which is pi into what? T on what? Tau. Okay, so this is how we write the rectangular pulse. Okay. Or you can also say that you can write rect like this. Okay, and then you can write T on tau. Okay, T on tau like this. Okay, so this is the rectangular pulse. Okay, so a pulse means that it comes just once before it may come again. Okay, so this is it. Okay, so here is what? 1. Here is 0, and then here is minus tau on 2. Here is tau on what? 2. Okay, so here is t, and then this is a rectangular pulse. Okay, so let us see how we can be able to deal with this one. Okay, let's see how we can deal with this one. Okay, so now for Fourier transform of this one, it is going to be, so let's say Fourier transform of this one, let me write here, let's say rect, okay, t on what? Tau, okay, as is normally denoted. Okay, it's going to be equals to here infinity minus infinity. Okay, so let's say rect t on tau, okay, into e exponent what? E exponent minus j omega t d what? dt. Okay, so basically this is going to be for it, and it's going to be for the interval minus tau on 2 less than t less than what? Tau on 2. Alright, so this is how it's going to actually be like. Okay, this is how actually it's going to be like. Okay, so now basically you see that it's a square wave. It's not a square wave, sorry, it's a pulse. So if it's a pulse, this space becomes what? 1. Okay, so in that case, then I'm going to have, if this place becomes 1, I'll be left with only this one. So I'm going to have minus infinity. Sorry, it's not going to be minus infinity. All right, it's not going to be minus infinity because right now I have limit for it. Okay, and what are those limits that I have? Okay, the limits are minus pi on 2 and then pi on 2. So here I'll write minus, the limits are minus tau on 2 and tau on 2. So minus tau on 2 and here positive tau on 2. Okay, and then here is 1. Okay, because it's a pause. So if it's 1, then I'll be left with only this one. So minus j omega what? T d what? dt. So this is what I'm actually going to have. Okay, so if you do your integration, then you're going to have minus 1, okay, over what? J omega, okay, over j omega, on j omega, okay, into what? E minus j omega what? T, limit what? Minus tau on 2 and then tau on what? 2. So now let's introduce our limits and then let's see what we get. So if we introduce our limit, I'll get minus j on what? Omega, minus j on omega. Okay, I'll get minus j on omega into what? Into e exponent what? Minus j omega. Okay, here minus tau on what? 2, minus tau on 2. Okay, and then here sorry, please. It's always important that we introduce the upper limit first. Okay, so please, I'll make here positive tau on what? 2. Positive tau on 2 minus, okay, e minus j omega, okay, negative what? Tau on what? 2. Okay, so this is what I'm going to get. Okay, so if I do this, then I'm actually going to have minus 1 on what? J omega into what? Into e exponent what? E exponent minus j omega tau on what? 2. Okay, tau on 2. And then minus e exponent what? Positive j omega minus positive. Okay, tau on what? 2. Okay, so this is what I'm going to have. Okay, this is what I'm going to have. Okay, so now if I have this, I can now multiply through by this negative. So if I multiply through by this negative, this one is going to come here. So I'll have e, this one will be positive now because I'm multiplying through by this what? Negative. E j omega tau on 2, and this guy will become negative now. E j minus j omega tau on what? 2. Okay, this is what I'm going to have, and this guy can now come down. J what? Omega. Okay, so basically this is where we can actually what? Arrive. Okay, but you can now, from now, you put in your sine, your sine and your cosine. Okay, so if you put in your sine and then your cosine, then you're going to have cos omega tau on 2. Okay, cos omega tau on 2 plus j sine omega tau on 2. Okay, minus cos omega tau on 2. Okay, and then here it's going to be minus, so it will be what? Plus j sine omega tau on what? 2. Okay, so you see that this guy will cancel what? This guy. And then you're going to have 2j sine omega tau on 2. Okay, over what? J omega. Okay, so now what you're going to have is that this is what you're going to get. So now you're going to have j can cancel j. You're going to have 2 sine tau what? Omega on what? 2. Okay, over what? Over omega. Okay, this is what you can have. Okay, but what happens is that we can be able to write this function in terms of what? Sinc. Okay, when we say sinc, sinc is such that sine theta over what? Theta, which is also equals to, let's say, sine what? X over what? X is equals to what? Sinc what? It's equal to what? Sinc X. Okay, or in this case is what? Sinc what? In, from here also is what? Sinc what? Theta. Okay, so we can also write this one in this particular what? Format. Okay, in this particular format. So let us see how we can be able to represent it in this sinc format also. All right, in this sinc format. All right, so that one will not be much of a hurdle for us to cross. We're going to see it. Okay, so putting it in terms of sinc, what I'm going to have is that I'm going to have sine, okay, omega tau on 2 over. You see that, and here is what? There, wait, please. Okay, so I hope you can see from here. Okay, sine omega tau on 2 over what? Omega. Okay, so this tau has to what? Come here. Okay, and then this two, which is here, okay, is going to come down here. Okay, it's going to come down here. Okay, there was already omega here, so this omega here it is. Okay, and then this two here, this omega here it is. This two here, it has come down here. Now there is what? I've introduced a tau, but there is no tau here. That means that I have changed the equation a little bit. Okay, so to get the original equation back, I must multiply here by tau. Okay, so now you can see that this is in the form of what? Sine theta over what? Theta. Okay, so this is what gives us the what? The sinc what? Function. Okay, this is what gives us the sinc function. Okay, so now if you actually have this one, that means that you're fitting it in terms of what? In terms of the what? Sinc X or sinc what? Theta. Okay, so here what I can do from here is that I can just plot my graph for the sinc that I have here. Okay, so let's see. Okay, okay, so here is equals to, let's say, sinc what? Theta. Okay, all right, so here in terms of the sinc graph is actually of this particular sort. It's a kind of decaying graph or decaying signal. Okay, so here is what? Omega, because it's Fourier what? It's Fourier transform. I found the Fourier transform. If you find Fourier transform, that means that it's been changed to the what? To the frequency domain, so it becomes omega. Okay, so the sinc function is something of this particular nature. Okay, it's a kind of decaying, a decaying wave. Okay, all right. So here becomes what? X is, we found the Fourier transform. So here becomes x of what? Omega. Okay, so now here in terms of the sinc, okay, whatever you have here is equals to what? N pi. Okay, it's equals to n pi. So here I'm going to have omega tau on what? 2 is equals to what? N pi. Okay, that is equals to what? N pi. So now I'm going to find omega. Okay, so now here this one can go here and this one can what? Divide. So now from here what I can say is that omega is equals to what? 2n pi on what? On tau. Okay, so that means that this place, okay, that means that this place is going to be what? This place is 1, so it will be what? 2 pi on what? Tau. This place is what? 2, so it will be what? 4 pi on what? On tau. Okay, 4 pi on tau. Okay, so it's going on and on. Okay, so this place is what? 0, and then this place is going to be what? This place is going to be minus 2 pi on what? Tau. Okay, here is going to be what? Minus 4 pi on what? Tau. It goes on and on and on. Okay, then in that case, what happens here is that sync 0 is always what? 1. Sync 0 is always what? 1. So now, if sync 0 is 1, here this place is what? Sync. This place is what? 0. So if sync 0, this place is always 1, then if I put sync 0 over here, you see that then basically I'm going to get what? Tau. Okay, I'm going to get tau, because if here I'm saying that sync 0 is 1, then if I put 0 here, then sync 0 becomes what? 1. 1 times tau, that means that here becomes what? Tau. Okay, because we're saying that sync 0 is what? 1. Okay, so now that means that the whole sync 0 here, this place will become what? 1. 1 times tau becomes what? Tau. So here becomes what? Tau. Okay, so that is how you can actually solve this question. Okay, this is how you can solve this particular question. So now, what I can now say in terms of summary of this question is that Fourier transform of rectangular pulse. Okay, Fourier transform of rectangular pulse, which is t on what? Tau. Okay, is equals to tau into what? Here is sync. Okay, sync what? Omega tau on what? 2. Okay, so this is the what? The Fourier transform of a rectangular pulse. Okay, so I can also write it this way. Let's say rectangular pulse, tau on t on what? Tau. T on tau. Okay, the Fourier transform rectangular pulse is what? Tau into what? Sync what? Omega here is going to be tau on what? 2. Okay, so basically that is how you can just do it. Okay, and then I think there's also another way that you can actually do it. Okay, so let me show you the other way that you can also do it. Okay, you see that this is the rectangular pulse. Okay, and then it's like this. Okay, let's say here is A, and then here is minus what? Tau on what? 2. Tau on what? 2. Here is what? 0. Okay, so let's find its Fourier transform. Okay, from this. Okay, so now basically what you're going to have is that you're going to have the area. So what will be the area? The area is from here to here times here to here. What is here to here is what? Minus tau on 2, tau on 2. That means here to here is what? Tau. Here to here is what? A. Okay, so I'll have what? A tau. Okay, into what? Sync. Okay, into sync. So now the sync, the first thing you have with respect to the sync that you write is what? Your W. Okay, your W and into what? Half. Okay, into half of the width. Okay, and what is half of the width that we're talking about here? Okay, half of this place, half of this place is what? Tau on 2. Okay, which is what? Tau on 2. So basically that's how you can also solve it very simply. So this brings us to the end of this particular session. Thank you and see you in the next class.